Next topic is of magnetic flux and magnetic flux density. In a free space, consider define what is our magnetic flux density is of. The representation is of by the letter of B. I already shared the how what are all the alphabets will be using, in which way we will be using, for which factor it will be using. For one sheet I already shared. You just go through that one or thrice. If you just go through that sheet what I shared, it will be easy for you which parameter is telling what uh, things in our magnetic field that will be giving information for us. Okay, then magnetic flux density is defined as, that is B is going to be, that is mu naught into H in the free space only, where B is the measured in the Webers per meter square, or in terms of one more unit, that is newer unit adopted in terms of international systems, that is called as a Tesla. The person invented, for that reason we given the name as a Tesla. The magnetic flux density is going to be measured, we can measure by Webers per meter square or else by and Tesla. Nowadays we will be using of Tesla only. An older unit that is often used for magnetic flux density is by using of the Gauss, that is G. Okay, then where 1 Tesla or 1 Weber per meter square is same as that of 10,000s of Gauss. This is what the relationship between our Tesla to the Gauss, or else from Weber per meter squares to the Gauss. Then what is the constant mu naught is not a dimensionless and has a defined value for the free space, the value, and it is measured in terms of Henry per meter. This you will know. That is mu naught is going to be 4 pi into 10 raised to minus 7 Henry per meter. The name mu naught is nothing but our permeability of the free space. Then our H, that is our H is of what? Magnetic field intensity. E is magnetic electric field intensity. H is magnetic field intensity, is measured in terms of amperes per meter. The Weber is dimensional, equal to the product of Henrys and amperes, H into with the current. Then considering the Henry as a new unit and the Weber is merely a convenient abbreviation for the product of Henry and amperes. Instead of going for Henry with the amperes, we will be using of the Weber. That is what here it is telling. Then when time varying fields are introduced, when we are going to be considering of time varying fields, it is shown that the Weber is also equivalent to the product of volts and the seconds. Volt second. That's what here it is telling. When time varying fields we will be considering, instead of going for Weber, we can take off voltage into time. Then the magnetic flux density is a vector, that is B. Observe here, whatever we are taking, it's mentioning is a bold letter, means it is a vector quantity that you have to keep in mind. Then as the name Weber per meter square meter implies, is a member of a flux density family of a vector field. One of the possible analogies between electric and magnetic fields compares the law of, here we are going to be comparing the law between a Biot-Savart's and also about the coulombs, and analog between H and E, that is magnetic field intensity, and to the electric field intensity. The relationship is going to be like this, that is B is going to be mu naught of H and D is going to be, we know that it is of F long naught into E. Then the lead to the analog between our in terms of magnetic flux density and also electric field flux density. If B is a measured in terms of Tesla or Webers per meter square, you can write any one of these. If you write both, it's good. Then the magnetic flux should be measured in terms of a Webers. That's what they are telling. Then let us represent a magnetic flux by pi. Here we are going to be taking as pi and define pi as a flux passing through any designated area. Means our flux is passing through some area, whether it is this area, or I am going to be taking a cable which I may take with any of the magnetic field. path so that I can pass the current, and I'll be waiting of my magnetic field intensity due to the current. Based on that surface, then the equation is going to be pi is going to be equals to integration with that surface b dot ds in terms of Webers. Remember this equation. Then our electric flux, that is, this is one more notation, that is psi, measured in coulombs and of Gauss law, which states that the total flux passing through the any closed surface is going to be equals to the charge enclosed. This is what we already saw in terms of a Gauss law, right? The same thing here it is going to tell, that is psi is going to be equals to the closed integral of flux density. How much it's going to be depends on how many charges are enclosing of that surface. The same equation here it is taken. Then the charge Q is the source of the lines of the electric flux. Of course, how many for this area, how many flux are going to be based on how many charges are included on that surface, right? Is the electric flux, and these lines begin and terminate on positive and negative charges. It depends. Positive and negative charges means if it is a positive here and negative of here, when I take the charges like this, the field what it's going to be going for, it will be creating its own magnetic field. So it will be originating and terminating to the negative part. It depends how the which electrons is having most strongest path. Based on that it will be going for. Then now such source has ever been discovered for lines of magnetic flux, means we are not still we discovered of that part. In example of infinity long straight filament like your wire cable carrying the direct current I and the magnetic field intensity H, field form concentric circles about the filament. Like this it will be going on. Then our magnetic flux density B is going to be mu naught H. The B field is of the same form as it is going to be for the electric field intensity also. Then the magnetic flux lines are closed and do not terminate on a magnetic charge. Here it's not magnetic flux lines as electric field, it will be terminating, but here it is not going to be happening. It's not going to be terminating in the magnetic charge. That's what here it is telling. Therefore, for this region, Gauss law for magnetic field is going to be 0 only. That's what here it is telling. That is integration of closed surface flux density with that surface dot ds is going to be equals to 0. As in the electric field, it is going to be terminating it with the other side based on the charge, but in magnetic charge, it's not going to be happening. That's what here it is telling. Instead of q, it is going to be 0 in the magnetic field. Concept is simple. What we in the from the Gauss law, what we are telling, it is equals to the magnetic field flux. How much it's going to be? It depends on the charge, but in the magnetic field, it's not depends on the charge. Simple concept. What we take in the equation way. Then applying the divergence theorem, we know that the del dot B is going to be equals to 0. Then from this, what it is telling us from equation of these two, 35 and 36 here mentioning, it's not proving that what it is, but have only suggesting that the truth of these statements by considering a single field of infinite element. The infinite what's going to be carrying that part, infinite filament. It is also possible to show that based on these two equations follows from the Biot-Savart's law and the definition of B, that is B is going to be mu naught H, but is another proof is going to be taken in the next section. Okay, we are not going. Next, we will consider of the Maxwell's 4 equations as they apply to the static electric field and a steady magnetic field. Then the equations for here it is taken as del dot D is going to be equals to rho V, del cross E is going to be equals to 0, then del cross H is going to be equals to J, then del dot B is going to be equals to 0. This is what Maxwell's 4 equations. Next, this to these equations, what it is taken, 2 expressions related to our flux density and electric field intensity in terms of magnetic and also in terms of your electric field density, that is D is going to be, again writing the same equation, F log naught into E, and B is going to be mu naught into H. Then we know that is E is going to be, this part we'll discuss in the second module actually. Just remember here, that is field intensity in terms of electrostatic potential. E is going to be minus del into V. Then steady magnetic field, the discussing of this all taking based on the polarization and all, it's not required for us. Then from these four equations specifying the divergence and about the applying a curl of an electric and magnetic field, the corresponding set of four integral equations instead of it is in terms of your point form, in terms of integral form, in terms of static electric field and also about a steady magnetic fields, it is going to be integration of its surface d dot ds is going to be equals to q, that is nothing but how much the volume it is going to be enclosed, that is volume rho v into dv. Then about integration with closed surface e into dl is going to be line integral, here it is going to be taken as line integral, that is going to be equals to 0. In terms of magnetic field, integration closed integration h dot dl is going to be equals to current, that is nothing but integration s of current density j into ds. In terms of magnetic field density, integration closed surface with b dot ds is going to be equals to 0. Therefore we can use of any of the equation of point form or else in terms of a integral form. This was the same thing here it is written. With the good knowledge of the vector analysis, we can analyze how the equations we will be taking on which based on the condition of which material we will be using, how much the electric field density or magnetic field intensity it is going to be producing, and then which equation we will be using. That is also very important. By using of this Maxwell's equation in terms of point form or integral form, we can choose of that. The same thing here it is taken. Then some of the experiments are done to get this equation. So one example here it is taken as example used for flux and flux density in the magnetic fields. The find the flux between a conductors of a coaxial line. Here it's not taken. It is then the magnetic field density, that is it's given as h pi is going to be I divided by 2 pi rho, where rho is in between of A and B. Then B is going to be equals to mu naught h, that is going to be equals to mu naught into I divided by 2 pi rho into A pi. This equation, remember, this will be helping in solving of the problems. Then the magnetic flux contained between the conductors in the length d is the flux crossing any radial plane extending from rho is going it's like concentric ring only with a different radius. Some of the examples what is taken is same way. This may be A, it will be B only. The same figure actually here it is not taken. The figure is somewhere in the textbook for that reason. Then rho is going to be A and rho is going to be B. Then z is equal to 0 and to the z is equals to d. Then equation is going to be pi is going to be integration of its surface b dot ds is going to be, here integration will change. For rho it will be a to b and for z it is 0 to d. With the length d it is taken for that reason. Then substitute for b, mu naught I into divided by 2 pi rho into a pi, then d rho dz into a pi, this unit vector as it is. There is I can write here that this equation you have to remember, that is pi is going to be mu naught I into d divided by 2 pi ln b divided by a. This is the expression how it is going to taken for the inductance of the coaxial transmission line equation. Okay, just you have to remember the equation. In the question paper it is not asked about you have to write off about electric field flux, magnetic flux or magnetic flux density, but equations are very important how we are going to be taking. Remember the pi equation and psi equation. And what is the condition if I am going to consider for the magnetic field? Then taken of our uh, Maxwell's equation in terms of integral form and also in terms of point form. Then you write the equation of how, if I am going to take any coaxial line, what is the equation we will be getting out. You remember this equation part and this one. These two, if you remember, that will be enough. Okay, theory it is not in the exam, but you should know what are the equations. At least if you practice the equation, you can write the theory. Theory is not having that much importance here. Equations is gaining more marks for you. Okay, this is about a small topic about magnetic flux and magnetic flux density. Then about just here also again as a equation part will be continuing further. Okay, here it is a small table which gives the information about Maxwell's equation in terms of a static and magnetic fields. Here it is in terms of point form. The same thing what it is taken previously, here also the same. This is based on the Gauss law and second equation. It not non-existence of magnetic monopole. Then conservation nature of electrostatic field. With the third equation is going to be based on Ampere's circuit law. We will be adding of the four Maxwell's equation. Almost the Maxwell's equation will be playing in each and every topics what we are learning from first module to the fifth module. Okay, just you remember all the four equations of Maxwell's. That's it. That's what I can tell. Then we'll go with the one more topic. Again, it's not given in the direct equation, a direct topic in the exams, but you should know how a scalar quantity will be taking and vector quantity will be taking for any of the magnetic field. The problems were very important, which are in that topics are taken for us. Okay. Based on here, some of the electric field problems we say what it is taken they are telling, but we still not yet to complete second module. We'll learn of those in the next after this module. Okay. Electric potential V to the electric field intensity is nothing but is going to be minus del dot V, del of V. Dot if you tell it will be wrong for the test. Then we'll be defining for potential in terms of a magnetic field, magnetostatic field, that is B. In fact, the magnetic potential could be a scalar, that is Vm, or it may be a vector. Which one you have to take? That is what we from this will be giving the information about whether it is a scalar quantity or it's a vector quantity. Which one we have to take? Whether direction is important for us or is the value is important for the magnetic field. That's what here it is going to be defining now. To define Vm and A involves a recalling of two important equations those you can leave off. Then del cross del V is going to be equals to 0, whereas this for equations we know basically for first model only we learned, that is del dot del is going to be 0 only. Plus A is going to be equals to 0. Then any scalar field and a vector field is going to be the same equations is going to be holding for. Then E is going to be equals to minus del V. Then we define the magnetic scalar potential, that is Vm in amperes, as related to the H. What's the equation I can write here? In terms of magnetic field, that I can, instead of electric field, I can write here as H is going to be equals to minus del Vm. Here it is taken for the electric field density as V. Here it is going for magnetic field, it's representing as Vm. And if J is going to be equals to 0, that is current density is going to be equals to 0. Then the condition attached to this equation is important and it will be explained in the previous thing. Then J is going to be equals to del cross H, is that is going to be equals to del cross, substitute for H here, that is minus del Vm, that is again it's going to be equals to 0 only. Then Vm must satisfy the condition of this first equation. Then thus the magnetic scalar potential Vm is only defined in the region where J is going to be equals to 0. We can define for our voltage of magnetic field only when a current density is 0. Then about this equation, then we should also note that Vm satisfies a Laplace equation just as V does for electrostatic field. Therefore, what is Laplace equation is going to be? Everything it's going to be equals to 0 only. That is del square of Vm is going to be equals to 0. That's what we learned. Then where J is also going to be equals to 0. Then the magnetic field del dot B is going to be 0. Then based on this, the vector magnetic potential A in terms of Webers per meter, we can write here as B is going to be equals to del cross A vector quantity. Then I can tell that V is going to be equals to integration. This equation we already know, that is dq divided by 4 pi epsilon naught into r. Then for line integral, our A equation is going to be line integral, integration of with L mu naught I into di divided by 4 pi r for line integral. Then A is going to be integration with surface mu naught k into ds divided by 4 pi r for the surface current. Then for volume current, A is going to be integration with volume mu naught j dv divided by 4 pi r. The equations what it is taken from 4.1 to 4.3. It's derived from the V equation only. An alternate approach would be, you can write it off these things. Then about what is our B equation, that is our flux density, that is equal to mu naught divided by 4 pi integration with L I into di dash, here it is taken, then into cross with R divided by R cube. Then here the same thing what it is taken for in the Coulomb's law, here from O a distance with here the point from point field is kept, that is at the xy direction. Then the distance is r is taken r minus r dash. The distance from O to, you can take here point, if I'm taking as point P, then it is from O to P is of r and O to at for a small differential length. This is the element where it is going to be considering here, that is with the differential length is dl and current is going to be di only. Then here the position is going to be x dash y dash and z dash, and distance is of r dash only. The source point x dash y dash, and to the field point, this is a source point, and this is the field point, where r is the distance vector from the line element di dash, then dl dash you have to consider here. Then at the source point x dash y dash and the z dash to the field point xyz, r is going to be, this we know that's about mod of r. Then r is going to be mod of r minus r dash. Then what is the equation we can write here? X minus x dash whole square plus y minus y dash whole square plus z minus z dash whole square, that power is going to be 1 by 2 only. Then del of 1 by r is going to be x minus of x minus x dash ax plus y minus y dash ay plus yz minus z dash az divided by the whole r cube, that is x minus x dash whole square plus y minus y dash whole square plus z minus z dash whole square, that square. Then power 3 by 2 I'll be getting as minus r by r cube only, or else we can write here as r divided by r cube is going to be minus del 1 by r, that is nothing but ar divided by r square only. Then differentiating is with respect to x, y, z. Then substituting for in the equation, then I'll be getting as our flux density is going to be magnetic flux density here. B is going to be minus mu naught divided by 4 pi integration with line integration L I into di dash into del 1 by r. Then we applying a vector identity, that is this is like a formula for us. Del cross f into f is there, I can write here as small f, del cross f capital F plus del f cross with capital F, where f is a scalar and capital F is a vector quantity. Here small f is going to be in this equation 1 by r and capital F is going to be di dash. And if I substitute here, I'll be adding as minus del 1 by r into di dash, that is going to be di dash into del 1 by r, that is going to be 1 by r del into 1 by dl dash minus del dot cross di dash divided by r only. Then del operator with respect to xyz, and where di dash is a function of x dash, y dash and z dash, then del cross di dash is going to be equals to 0. Then di dash cross with del 1 by r, that is going to be minus del cross di dash divided by r. Therefore, the equation of this is going to be reducing to the equation, that is b is going to be del cross integration with a line integration, then mu naught I into di dash divided by 4 pi r. Then comparing the equation 7.50 and 7.39 of this equation here, then I can write here as a is going to be integration, line integration L mu naught I into di dash divided by 4 pi r only. Therefore, applying the Stokes theorem here, then psi is going to be equals to surface integral b dot ds. I can write here as integration, surface integration del cross a, that is nothing but dot ds is nothing but closed integration L a into dil. So di here. Then about psi is going to be, I can write here as closed integration a into di only. Then therefore, what it is telling us, magnetic flux through a given area can be found. We can use of equation of 7.32, that is not taken here, or else it's we can use of this equation. Then the magnetic field can be determined by using of either I can use of Vm as scalar quantity we can use, or as a vector quantity we can use to find our magnetic field. It's not that it should be a scalar or it should be a vector quantity. The choice is dictated by the nature of the given problem, which problem it is given for us, that Vm can be used only in the source free region. This is one small point we have to remember, where we can use of this at Vm, where it is going to be taken, it is for the free region only, source free region, then we can use of the scalar quantity. The use of the magnetic vector potential provides a powerful vector quantity if I am going to be preferring a powerful and elegant approach to solving of electromagnetic field problems. Particularly, we'll be using relating to the antennas only. This is what about our whether it is of a magnetic field or electric field. Here, as per examination point, you have to remember the equation. Now, derivation is important here. Actually, this based on this topic, a problems will be given for us. We have to find it whether it is a scalar quantity or a vector quantity. If it is that, then we have to find what is the scalar value and a vector value. If we go through the structures will be given for us, for that structure we have to find how what is the whether it is scalar or vector of a magnetic field of that. Okay, if we solve a problem, then you'll understand what are the equations is going to be. Just by taking the equations, it's I know it will be difficult to analyze. We'll take the problems in the next class, then we will understand what is the, if I compare with the equation, then it will be easy for you to understand of this topic. Okay.